So now if we put all that together, we see that volume is inversely related to pressure, Boyle's law. We see that volume is directly related to the absolute temperature, Charles's law. And we also know that volume is directly related to the number of moles, which is Avogadro's law. Gay-Lussac's law is pressure and temperature, so we're trying to relate everything to volume here, so that's why that one's omitted. But if we put all these things together, we end up with a formula where volume is directly related to moles, directly related to temperature, absolute temperature, indirectly related to pressure, and then there's some constant here that relates them all to each other. So volume is directly related to moles, temperature, indirectly related to pressure, and there's some kind of proportionality or constant, since there's a constant. So obviously volume is not equal to that, but it's proportional to or related to NT over P. So actually, if you plug in 1 mole and you plug in standard temperature and you plug in standard pressure, and since we know the volume is 22.4 liters, we can solve for what this R is. So R is called the proportionality constant, and it's also sometimes called the ideal gas constant. And so R has a specific value. So like I said, you can use Avogadro's law, which states that 1 mole, so if we put 1 in for N, and we put in 22.4 liters for volume, and we put in standard pressure, 1 atmosphere, and we put in standard temperature, 273 Kelvin, and we solve for R, we get this value, 0.0821, and the units are liters times atmospheres divided by mole divided by Kelvin. And it's just the value for R. So we like to be elegant and write R instead of 0.0821. But anytime you have R in an equation, you just plug in this number. And notice the units are kind of funky. These are the absolute units. You can get other values for R that have other units, but since we're talking gas laws with pressure and atmosphere and temperature and things like that, these are the units. We're going to use this number with these units. So if we rearrange this equation, we get what's called the ideal gas equation or the ideal gas law, and it's PV equals nRT. Again, P is pressure, and because we're using this value for R, and because those units are very specific, this time pressure has to be in atmospheres. You have to convert to atmospheres if you're not given it already. Volume has to be in liters, again, because R is in terms of liters. N is the number of atoms, and we use moles as our unit, moles. And then R is that number, 0.0821 liters atmosphere divided by mole divided by Kelvin. And then, of course, temperature, and temperature always has to be in Kelvin, so temperature in Kelvin. So we can solve other types of problems. So far the problems we've looked at have been, let's change this condition, let's change that condition, and so those were changing conditions, and we could find the second set of conditions if we knew the first set. But this one could apply for any gas. As long as you know the pressure, temperature, and volume, you can find out how much you have by using this equation. So let's just look at a quick problem. An experiment calls for 3.5 moles of chlorine gas. What volume should I measure at 34 degrees Celsius and 2.45 atmosphere? So to know that I have that many moles. All right, so I know PV equals nRT. This time, because I'm looking for volume, I'm going to solve the equation for volume, nRT divided by P. Again, make sure that our temperature is in Kelvin. So that would be, let's change that to yellow. That would be 307 Kelvin. We want to make sure our pressure is in atmosphere, which it is. That will give us our volume in liters. And we want N to be in moles. So if we plug that in, we have N is 3.5 moles, R is 0.0821, T is 307, and P is 2.45 atmospheres. And look what happens here as the units, because this is that funky units, what happens is Moles will cancel. Atmospheres, you've got one in the numerator, one in the denominator. Now Kelvin here is in the denominator and the numerator. So everything cancels out except for liters, which is then my answer. So volume is 36 liters. So I would need to measure out 36 liters, and if it were at 34 degrees Celsius and 2.45 atmospheres, I would have exactly 3.5 moles. So that's a very simple problem there. We know the moles between mass and moles. We know that molecular weight, usually we look at it this way, molar mass or molecular mass equals the number of grams per mole, right? So the mass divided by the moles. So we can rearrange this equation. That's where we get this. Moles equals grams divided by molecular weight. Mainly, if you want to find the molecular weight and you know the grams and you know the moles, you plug that in. If you're trying to find moles, you can take grams divided by molecular weight. That's how we use that in an earlier chapter, but this relationship holds. Now, we can actually, what we're going to do, and a lot of times mass, of course, mass is given the unit m, and molecular mass or molar mass is given that symbol, mm. So we can actually, and remember moles is N, so we can actually plug that in. So N equals M over MM. So if we plug in little m over mm into our PV, so PV equals N RT, but N is M over MM, and then rearrange this equation, we get another, this is also the ideal gas law, but it's in different terms. So we can actually find the molecular mass of any gas if we know its mass, and if we know its temperature, its pressure, and its volume. So just another use of it. One of the labs we do uses this. We weigh the mass of the gas, and we know the volume and so forth, and plug it in this equation. So let's do an example here. We have a 15.5 gram sample, so that's our mass, of an unknown gas. It has a volume of 5.75 liters. And again, don't forget, since we're using R, we have to make sure that now this time, grams will cancel a different way, but we want volume in liters, pressure in atmospheres. And we always want temperature in Kelvin, so just keep that in mind. Some of my problems look like they're too easy because I've already got it in atmospheres and I already have it in liters. And there's the temperature, so we just have to add 273, which makes that 298 Kelvin. So we want to know what its molar mass is. So we can use this equation, and we're going to plug in the mass, 15.5 grams. We're going to plug in R, 0.0821. We're going to plug in temperature, 298 Kelvin, the pressure, 1.08 atmosphere, and the volume, 5.75 liters. Again, let's look and see what happens to the units. Liters cancel, atmospheres cancel, Kelvin cancels. This time, our units will be grams divided by moles, moles in the denominator. So that's the unit, that is the unit for molecular mass or molar mass, is grams per mole. So everything else cancels, and we get 61.1 grams per mole. So we could probably identify what the gas is because we may know approximately the formula or something. But this is just a variation on the ideal gas law. We can do one more little derivation on the ideal gas law by saying, so here's our going back to the ideal gas law. PV equals nRT, m over mm for n, and if we rearrange it a little bit more, we know that density equals mass over volume. So if we rearrange this one more time, solve for mass divided by volume equals density, then we can rearrange this equation one more time, and density is the pressure times the molecular weight divided by R divided by T. So that's just another version of the ideal gas law. And you can actually do problems using the ideal gas law without ever deriving these other ones, but these sometimes make them a little easier if you're if you're trying to find the right formula, the simplest formula to use. So let's calculate the density of ozone. Ozone has the formula O3, which means its molecular weight is 48 grams per mole. At 50 degrees Celsius is what we want to calculate it at. So 273 means 323 Kelvin. And at 1330 torr, so there I made one where it's not atmosphere. So before we do anything else, we have to convert torr to atmospheres. And remember that 1 atmosphere equals 760 torr. So we just take our torr divided by 760. If this was millimeters of mercury, the same thing, we divide by 760. So our pressure is 1.75 atmospheres. You have to convert. Whenever using R, you have to convert volume to liters and pressure to atmospheres. So now we know that density equals pressure times molecular weight over R over T. Just plug those numbers in. Our pressure, 1.75 atmospheres. Our molecular weight is 48 grams per mole. R, 0.0821 liters atmospheres mole Kelvin. And our T, 323 Kelvin. Again, the Kelvin will cancel. The moles, we have one in the denominator here, so they're both in opposites. The atmospheres will cancel, numerator, denominator, and our units will be grams divided by liters. So that's the density of ozone at 50 degrees Celsius. So I hope that makes sense. Up there, showing you everything canceling, although they don't line up very well. Okay, let's talk about partial pressures. Partial pressures is an interesting thing about that's not going to be the same for liquids or solids, but it works really well for gases. So we can actually use the ideal gas law to pertain to mixtures of gases as long as the gases don't react each other. So Dalton's law of partial pressure says that if you have a bunch of gases all in the same container, then if we take the pressure of each gas and add them all together, we'll get the pressure of the total pressure. So that kind of makes sense. So if we had a mixture of A, B, and C, we add the pressure from A plus the pressure from B, which is a partial pressure, and the partial pressure from C, add those together and we get the total pressure. You know, if you think about our atmosphere, let's say standard atmosphere is 760 torr, or 1 atmosphere. Well, maybe most of it's nitrogen, so maybe I can't come up with numbers quick enough. Maybe 650 of it is nitrogen, and maybe another 80 is oxygen, and maybe another, they're not going to add up exactly because there's a whole lot of gases, and maybe another 20 is carbon dioxide, and so forth. So they all add up to 760, but each gas can have its own partial pressure, or the pressure if you were just to measure that one gas and add them together, and you get the total. So here's just another example. Here we have flask A with some helium in it, and the helium is 152 millimeters of mercury. And here's another container with 608 millimeters of mercury of hydrogen. And then what they did is they're adding oil to this funnel, so they're filling it up. And because it's sealed, all the gas molecules are going to go through the tube and into this container. So now over here, this is totally empty, and both gases are in this same container. And you can see still the helium still has a pressure of 152, and the hydrogen has a pressure of 608, but the total pressure is 760 now, and that's PT is the partial pressures added together. It doesn't have to be 760, this just happens to add up to 760. A lot of times if you have a gas, we can describe the concentration in terms of mole fraction. So this is a new unit. Mole fraction is given the symbol X, and sometimes we'll write like if there's 2 parts to it, we'll say XA and XB, and if there's a third one, XC, and so forth. So the mole fractions of A, B, and C. A mole fraction just equals the moles of that compound. So if we're saying the mole fraction of A, how many moles of A are there divided by the total moles. So if there's you know, if you have moles of A and you have the moles of B and the moles of C, that would be the total moles. So the mole fraction of A would just be the moles of A divided by the total moles. The moles of B would be the moles of B divided by the total moles. That would be the mole fraction of B. And then the mole fraction of C, of course, would be the moles of C over the total moles. So they would all add up to 1. The mole fractions would all add up to 1. Well, what they're saying here is that we can actually relate it to pressure. So mole fraction is also equal to the pressure of just A divided by the total pressure. And it's going to be equal to the mole fraction. So if we rearrange that equation, we can see that the partial pressure of one gas is equal to the total pressure of all the gases times the mole fraction of that gas in particular. So we can actually apply this to the ideal gas law, and if we're able to treat each gas independently, then we can say the partial pressure of one is times volume equals the moles of A times RT. Now we're not really going to do that much, but it's just something to keep in mind. That we can do it, especially if you go on and take some more chemistry or organic chemistry, we kind of have gases that we separate this way. So it's just helpful to know. All right, so let's just do a simple example of that. Let's say we have a mixture of gases in the atmosphere. All right, so we're just going to do nitrogen, and we got lots of other gases. So they're not worrying about that, but they're saying, okay, our total pressure is 760 torr. And they're saying, okay, what is the partial pressure of nitrogen if we know that the mole fraction of nitrogen is 0.7808? So if they're able to measure it and say, well, this is the mole fraction, so what is just the partial, what is the pressure just due to nitrogen? And the temperature doesn't matter, but I mean, it does matter because the mole fraction may change at different temperatures, but in this case, since it's not really involved with anything, they're just telling us. They're just telling us this is the mole fraction at this temperature, so what's the partial pressure at that temperature? And it's not critical because we won't find an equation with temperature. All right, since we know the partial pressure of nitrogen is just equal to the mole fraction of nitrogen times the total pressure, we just do that calculation. So the partial pressure of nitrogen is equal to 0.7808 times 760, or 593 torr. So I wasn't too far off on my guess on that previous slide. Nitrogen is about 593 torr. This is just some information. Not sure if we'll do a lab like this. There's a virtual lab I've done where we watch someone do it, but a common way to collect and quantify gas produced in a chemical reaction is to capture it in a bottle that's been filled with water. So I've got a picture on the next slide that you can look at it. And then if you hold the volume of that container and get it just right, then the pressure in there is equal to atmospheric pressure. And so you can know what the pressure is. But the problem is that as the gas travels through the water, it picks up a little bit of water vapor. So it turns out that some of the vapor, most of the vapor will be the product that you're trying to catch, but there might also be a little bit of water in there. So you have to do it like a calculation to subtract it out. So here's what I'm talking about. So here's the reaction happening, and there's a gas being formed. And the gas is, instead of collecting it directly into something, it's going through this tube, and it's being collected in this bottle. Like this is open because it's in water. So there's water in there, but the gas, it was totally filled with water. And then as the gas comes in, it displaces the water. And so this is the gas that's being collected. But what's happening is some of the water is turning into vapor. So inside here is actually the gas we're trying to collect, and then a little bit of water vapor as well, which is fine. The total pressure inside that container is equal to the pressure of the gas that we're trying to collect plus the gas of the water vapor. So let's say we're collecting hydrogen gas, then both would be the pressure, the total pressure inside that system would have both of those. So if we know that the atmospheric pressure, that's going to be equal to PT if you kind of make sure that the volumes are equal on your if you line up the volumes of the water inside the container and the collection thing, then the total pressure inside the beaker. If you so here's the thing: if you line up the water and the container, I didn't do a very good job of that. The water inside this and the water inside here, if you line them up, then the pressure in here is equal to atmospheric pressure. So that's atmospheric pressure. And then water pressure, or water vapor pressure, can be looked up, that whatever it is can be looked up on a table or graph, because it'll be at that specific temperature. So you can always find out what pH2O is. So if you subtract the total pressure, take the total pressure and subtract the pH2O, then you'll get the pressure of the gas in question. I don't think we're going to be doing this, but it's just kind of an interesting, easy way to collect a gas, but it's not always as easy as it seems. So we can find the pressure, and if we needed to find out something else, then we would have the pressure of that gas. So what I wanted to show you here, this kind of goes back to chapter 4. And I just wanted to review a few things. So if you remember, the key thing in if you're doing any kind of stoichiometric calculations, if you know the moles of one compound and you want to find the moles of another, you have to use that mole-to-mole ratio using the coefficients of the balanced equation. And so far, back in chapter 4, and actually earlier, so we learned about molarity back a couple of chapters ago, and we know that if we have the volume of solution and we use the molarity, we can find moles of A, because we know moles equals molarity times volume. We also know from the last chapter, and maybe one before that, that if we know the mass of the compound, we can use the molar mass or the molecular weight of that to convert to moles. So, right, so moles of A, or grams of A times grams per mole, molecular weight in grams per mole, will give me moles of A. So that's just another way. So if we know volume, we can find moles. If we know molecular mass, we can find moles. Now we have one more thing that we can add to it. And we also had that density on, I showed you a slide in the last chapter. But anyway, now we know the gas law. If we know the volume of a gas, then volume and moles are related. So if we know the volume of a gas and we know its pressure and we know its temperature, then we can also figure out how many moles it's equal to. So this is another stoichiometric way. Now, once you convert to moles of B, you have lots of options again. If it's a solution and we want to know the volume of B, then we can use molarity of B. If we need to know the mass of B, then we can use the molar mass of B to convert to grams of B. Or if it's another gas, then we can convert to volume of the new gas, again, by using PV equals nRT. So the key thing here is the mole-to-mole ratio to convert one to the other. And you never want to forget that mole-to-mole ratio. But now we have lots of ways to figure out moles, and we have lots of things we can calculate once we know moles. So I think I have an example on the next slide. Yes, so safety airbags in cars are inflated by nitrogen, and some of them will have this reaction. The rapid decomposition of NaN3, sodium azide is what that's called. So sodium azide, when it's hit, will break apart into sodium metal and nitrogen gas. The nitrogen gas will then fill up the bag. Well, here's the problem. We want to make sure that we know exactly how much NaN3 to put inside the airbag for it to react so that it totally fills up that airbag. Let's do the yellow. Right? If we don't put enough NaN3, then not enough nitrogen will form and our airbag won't open up. It'll get too little. If we put in too much NaN3, our airbag will explode and that won't do us any good. So we want the exact amount of NaN3 that will exactly fill up the airbag. So let's look at this question. So an airbag has a volume of 36 liters, or in this case, this airbag does. It has to be filled completely with nitrogen gas, and we want the pressure to be 874 millimeters of mercury, and the temperature will be about 26 degrees. So they're giving us those parameters. So the question is, how much NaN3 do we need to have to make this true? So how many grams of NaN3 must decompose to fill the airbag completely? So again, the key is, now here, if you look at this question, so we know our volume of the airbag, of the nitrogen, we know the pressure, we know the temperature. So knowing all those things, we can find out how many moles of nitrogen will fill up the tank, but that's not going to help us. We want to know azide. So then, once we know the moles of nitrogen, we can use the mole-to-mole ratio to find the moles of NaN3, and then we can convert that to grams to find out what it is. So again, if you look on that previous slide, we're using the PV equals nRT to get moles of A, which is the nitrogen, because that's what we can find, and then we're converting it to NaN3, but this time we don't care about, it's not a gas, so we can't use the gas law, but we can convert it to grams. So using that stoichiometry map. All right, so PV equals nRT, and we know how many moles of nitrogen are needed to fill the airbag. Since we're using PV equals nRT, pressure has to be in atmospheres and volume should be in liters. Well, they told us the airbag was in liters, 36 liters. But let's convert. First, we have to convert millimeters of mercury to atmospheres. So 1.15 atmospheres. And we also know 36 degrees, 26 degrees plus 273 gives us 299 Kelvin. So temperature, 299. So we rearrange and solve for moles of nitrogen. Pressure, 1.15 atmospheres. Volume, 36 liters. R, 0.0821. T, 299. So the first thing we found here, in order to fill up the airbag, we need 1.69 moles of nitrogen. And that's very helpful information, but it's still not what we're looking for. So now we can use our mole-to-mole ratio, 1.69 moles of nitrogen. We know we need 2 moles of NaN3 for every 3 moles of nitrogen. So that would be 1.69 times 2 divided by 3 gives me 1.13 moles of azide, sodium azide, and then if we multiply by the molecular weight of sodium azide, then we can find out how many grams of sodium azide we need to measure out. So I hope that makes sense. Stoichiometry always has this mole-to-mole ratio involved. Doesn't matter how the moles are gotten or what you do with the moles after, but that's the key right there. Lots of different ways to find moles, lots of different ways to use the moles and convert it to something else.